In this video, we'll continue our journey towards Stable Diffusion. In the previous video, we saw how to build a latent diffusion model. And now, we'll see how to condition it. We'll first dive into class conditioning on the simple mnist dataset and condition our LDM on the classes of digits. We'll then move towards image conditioning, specifically spatial conditioning, and we'll condition on the segmentation masks of celeb dataset and see results of that. We'll also get into how the same spatial conditioning is used for super resolution and inpainting tasks. We'll understand cross attention, which is what is used for text conditioning, see how it's implemented, and train on captions of celeb dataset and check out the results of that. And at last, we'll understand how to move from this text condition LDM to stable diffusion. But before we get into conditioning, let's first do a recap of what we have done so far. We implemented an unconditional LDM by first training an autoencoder to convert the higher resolution image in pixel space to a smaller resolution image in latent space. To train this, we used reconstruction, perceptual, and adversarial loss. Then we trained a diffusion model to generate images in this latent space. During inference, once we got our latent image, we feed it to our decoder to generate the image in pixel space. For the diffusion model, our choice was a unit, with these down blocks which downsample the input, mid blocks which work on the same resolution, and up blocks which upsample the inputs. And each block was a combination of ResNet and self-attention block. The time step information, which is required to give the model a sense of how much noise is there in the image, was added to these ResNet blocks after going through some projection layers. All of this we have already seen in detail in previous videos. And in case you haven't seen those, specifically the DDPM implementation and part 1 of Stable Diffusion, I would suggest to see them first before going ahead with this video. Now let's get into class conditioning. Our objective is that when we are generating latent images from random noise, we want to have our diffusion model generate outputs that belong to the class that we have provided. We'll do this on mnist dataset and see how to condition it on the class label of digits. So for any conditioning, we really just need two things. Transform the conditioning information to a representation that can be used by our diffusion model. And secondly, modify the layers of our unit to actually make use of that representation. For class labels, the first we can easily do using an embedding layer, which will be a number of class cross class embedding dimension matrix. So this will take our integer class labels and give us the respective embedding vectors as the class representation. This will be randomly initialized and we would be training this also as part of the diffusion training. For using this embedding representation, we actually do very minimal modification to the architecture that we already have. So all our blocks had layers of ResNet and self-attention, and we added the time step information to each ResNet block. And this was by projecting the time embedding through some linear layers and adding it between the conv layers of ResNet. For adding class conditioning, we latch on the same mechanism by which we add time step information. Just to refresh, for our time embedding block, we converted the time steps using sinusoidal embeddings, same as the original transformer paper, and then few FC layers. The output of this was the time step embedding. We first ensure that our class embedding has the same dimension as the time step embedding dimension. Then rather than passing the time embedding through FC layers and adding to each ResNet block, we first add the class embedding to the time embedding, and then pass this representation to the ResNet blocks. And the diffusion model, through the training process, will learn to use this class information to conditionally generate data. For all types of conditioning, we also want to ensure that the model learns to generate data unconditionally as well. If you know about classifier free guidance, then that use case is indeed one reason, but even without that, you would still prefer to have one model, which is capable to do both unconditional and conditional generation, rather than two separate models. And in reality, you might not even have labels for the entire dataset. So it would be great if the same model can learn to generate data without conditioning and simultaneously learn to use conditioning whenever provided. For training the model conditionally as well as unconditionally with respect to classes, one approach could be that if you have k classes, rather than having k labels, you have k plus 1 labels. And this k plus 1th class becomes sort of your null class. Then during training, we randomly switch the labels to this class. So for each of the k classes, the model will see class specific images, but for this null class, it will see all images and end up learning such a representation that allows the model to generate images of any class whenever this k plus 1th label is used. The other approach could be that we convert our class labels to one-hot vectors, and then for getting the class embedding, multiply this one-hot vector with this embedding matrix. And same as before, the two are added and passed through FC layers to ResNet block of unit. For unconditional training, you can just use the all 0 vector as the class label, which after the matrix multiplication ends up being equivalent to adding 0 in unconditional cases, which is kind of neat because rather than placing the burden of learning the representation of null class on the model, you are simply not giving any class information for the unconditional cases. And now this is exactly same as the unconditional diffusion model architecture, where only the time step information gets propagated to the ResNet blocks. Personally, I find this easier and intuitive, and this is the approach that we'll be implementing. So to summarize, for class conditioning, we have class labels as one-hot vectors, multiply these one-hot vectors with embedding matrix weight to get the class embeddings, add these to the time embedding right before passing them through projection layers and ResNet blocks. And finally, for also training the model to generate data unconditionally, randomly modify the labels to be all zeros. Let's look at the code for this class conditioning implementation. We'll first revisit our current version of code, which we had for unconditional LDM. And it's the same as last video, except that we are now using config files. So we had a dataset class, which just gathered all image file names from a particular path. And then in the getItem method, we get the image and just scale it from -1 to 1 and return that. Our diffusion unit model for its initialization required certain parameters, and we moved all of this to the config file, which now has all the necessary information within this LDM_param section. These are things like channels for down, mid, and up block, whether to use attention or not, or how many layers of ResNet and attention to use, and so on. This is the FC layers of the time embedding block, which take in the sinusoidal embeddings as input and generate time step embeddings that all blocks receive as input. And after that, we just have layers of down block, mid block, and up block. Let's also look at our blocks again. Down block was layers of ResNet and self-attention, and a downsample layer in the end. Mid block was first a singular ResNet block, and then layers of attention and ResNet. And remember, for all blocks, between the convolutional layers of ResNet block, we added the time step information. And this T_EMB_layers was the activation and FC layer which every ResNet block has to transform the incoming time embedding. Our up block in its input also received the same resolution's down block output. And after concatenating it with input and upsampling, we have ResNet and attention block. In the forward method of unit model, the first thing we did was convert from input channel to the number of channels that the first down block expects. Then this is where we first computed the sinusoidal time step embeddings and fed that to some FC layers to get our actual time embedding. And like we saw, every ResNet block's time step projection layer receives this as the input. We then call the down blocks, saving the outputs as they were required as input to up block, then mid, and then up blocks, with each up block receiving the saved down block output of the same resolution. And finally, output layers. This was our training script where we got everything from config, instantiated the dataset, our unit model, and the trained autoencoder. Let's straight away go to the epoch loop, where all we were doing was fetching images, encoding it using the trained VAE, randomly sampling noise, sampling time steps, and using the scheduler to add noise according to the time step to this latent image. And then train the model to predict the original noise using MSE loss. In our inference method, we first sampled a random latent noise, denoised it step by step using the scheduler and the trained unit model, and at the end used the decoder to convert the generated latent image to the generated image in pixel space. Okay, now let's see the actual changes for class conditioning. So this is the config for mnist, but for the unconditional model. And for class conditional LDM, the only change that happens is in the parameters of LDM. This conditioning info is what is added. And basically this captures every conditional aspect that is needed to initialize the model. So we have conditioning underscore types, which will be a list capturing the different conditioning the model should be capable of doing. At the moment for mnist, we only have class in here, and we'll expand this throughout the video. Then we have parameters necessary for class conditioning, which is the number of classes, and this cond underscore drop underscore prob. This is the probability with which we'll drop our conditioning during training. Like we saw, this is for ensuring that the model is trained to generate images without any conditioning information. And we'll drop conditioning 10% of the times. This is the only additional set of parameters that we require for class conditional LDM. In our dataset class, we also make minor modifications. It is additionally provided with the conditioning config. And then while fetching the mnist file names, we also get the class labels. The get item now returns the image tensor as well as this cond underscore input, which is a dictionary containing all conditioning information for this item needed during training. So as of now for mnist, we are doing class condition. So our cond underscore input will just have one key class, and its value will be the digit that this image belongs to. This if condition is just because the same code is going to be used for previous videos unconditional training as well. So it is just to ensure that the previous version also runs fine using the same dataset class. So if there is no conditioning required, we just return the image like earlier. Coming to our unit class, we still get all the parameters that we were getting from the config. This entire section is what we have added for class conditioning. And essentially it just takes the conditioning config that we saw earlier and fetches the number of classes from it. And then we use that to create our embedding matrix. And as we had seen, the dimension of class embedding is same as the time embedding dimension. So that's the only thing that will be added. Just a nn.embedding layer. Rest all same time embedding, down block, mid block, and up block. Our forward method will now receive this additional cond underscore input. And for class conditioning, we had seen that this is going to be one hot vector. And it will be the training code which we'll see later that will take care of converting the integer label that the dataset as of now returns to one hot vectors. So when the model receives the class input, it will actually be a one hot vector corresponding to the class label. Coming to the actual method, we had the first convolutional layer, and then we had the time embedding block, same as unconditional LDM. This is the new part where we take the matrix for embedding layer, and this line is just multiplying the one hot class vectors and the embedding matrix together to give the class embedding for all the batch images. And then like we saw, we added to the existing time embedding representation. This entire thing is the only change in the forward method. Post that, down, mid, up, and output layers are called. Let's also look at the changes in the training code. Main change is in the training loop. So like I had said, depending on conditioning mentioned in config or not, the dataset returns just the image tensor or image tensor and con_input. Then for class conditioning, we first take the integer labels, convert it into one-hot vectors, get the probability with which we want to drop this conditioning information, and then call this utility method. All this utility method does is for a certain fraction of batch, so according to our config 10%, it will convert the one-hot vector to an all-zero vector and leave the rest as it is. In the training code, that is all that is changed, so simply passing the one-hot vector additionally to the model. Then we do the same, sampling noise, sampling time step, adding noise, and training the model using MSE. In our inference method, we randomly get a set of class labels, convert them to one-hot vectors, and pass that as con_input, which then gets passed to the model's forward call. And for unconditional generation, we would just pass the all-zero vector here. So with these changes done, once we train a class conditional model on mnist, we get the following results. And here I have shown both conditional samples as well as a set of unconditional samples generated by a trained class conditional model. And the progress image is the original image prediction at each denoising step. Because of class information present when conditionally generating data, the model straight away has a decent original image prediction, like at t equals 1000 itself. Whereas for unconditional cases, that will happen only at like t equals 500 something. Also, for the unconditional samples, throughout the denoising progress, the class of digits will often change. But for conditionally generated data, the class for almost all the x0 prediction images remains the same. With class conditioning done, let's now get into image conditioning. And in this section, we are only focusing on use cases where we need spatial conditioning. So it could be the task of generating images conditioned on segmentation masks, or the task of super resolution, or the task of inpainting. For all of these tasks, the authors take the same basic approach of spatial conditioning, with minor changes for each of them. And also, the only change is what goes as input to unit. The architecture, as in the layers and blocks, remain the same. So up till now, we first take an image from the dataset, pass it to the encoder to get the latent image, and then our model gets a noisy version of this latent image as input. For spatial conditioning, for all cases, all we really do is concat the conditioning information to this noisy latent image and feed this as input to our model. As mentioned, there will be slight difference based on the task as to what exactly we concat. So let's first look at mask conditioning. Now assume we have k classes. So we concatenate all the masks for these k classes across channels. We then bring them down to the same spatial resolution as our latent image. These then go through 1x1 convolution to give us an output with certain number of channels, and let's say 2 for now. Then it's these 2 channels that are concatenated with the latent noisy image, and the entire diffusion model is trained on this input. Like we did for classes, here also we can zero out all the masks, which would lead the input that is concatenated to be all zeros if the bias is false for this conv-layer. And again, it's equivalent to concatenating zero conditioning information. And through training, the model will learn how to use this spatial conditioning and how to generate data when a non-zero mask is provided, as well as when this all zero mask is provided. In the official Stable Diffusion repo, when you will see model config for semantic synthesis, you will find the number of input channels to be 6. And this is precisely why. Because the 1x1 convolution, which is done by this spatial rescaler class, converts from 182 classes to 3. And the latent image is also 3 channel, so that makes the input to have 6 channels. I've only implemented this spatial conditioning, so let's quickly see that before moving to super resolution and inpainting tasks. I have trained mask conditioning using the celeb mask dataset. So this is the config for celeb dataset, and now this will be our conditioning config. Condition types list will now be just image. Maybe mask would have been a better name, but that's fine. The image condition config now has the input channels that the mask will have. So this would be the number of classes, and the celeb mask dataset has 18 classes excluding the background. We use the output channels to be 3. Both of this will be used for creating the 1x1 conv layer. Then we just specify the mask height, width, and like for class conditioning, we provide the dropping probability. Let's go to our celeb dataset class. So we get the conditioning config information, and then we fetch the images as well as the mask names. This is the labels for all the classes in our dataset in the right order. And then for each image, we get the corresponding mask here. Our get item will now get the image tensor and create the con underscore input for each item, just like we saw for mnist. And its value will be the mask tensor. The mask annotations that we get from here is actually a single channel image, with each pixel indicating the class of that pixel. Then this get underscore mask method takes that annotation mask and converts it into an image of dimension number of classes, cross height, cross width. For each kth class, we'll get the pixels having k value in the annotation, and those pixels of the kth channel of this image will be marked as 1. So the mask in con underscore input that the dataset returns for this case will be 512 cross 512 image with 18 channels. Coming to our unit, and all of this is the same as before. The change is actually in this part, where in addition to class conditioning, we also start handling mask conditioning. This we had already seen for the class conditioning case. And now for image, we just get the channels in mask and output channels for the 1x1 conv layer. And in this section, we create the new layers. This conv underscore input was already there, but for image conditioning, we first have a 1x1 conv layer to convert the 18 channels to 3. And this new conv input layer, which takes the 3 plus 3 6 channels as input. So 3 of the noisy latent and 3 for the output of 1x1 conv layer. So it takes the 6 channels and converts it into the number of channels that first down block expects. And that's it for the change in init. Same time embedding, same down, mid, and up block. In the forward method, this is the new part. Earlier we were just calling the conv underscore in, but now we first take the mask image, scale it to the same resolution as input latent, feed it to the 1x1 conv layer, and then concat this with the latent and pass it to the new conv layer that we created. After that, time embedding, class conditioning, down, mid, up, and output layers. All of these are the same. Let's also look at the training loop. We get the mask image and then do the same dropping of conditioning. This is similar to the class case. It's just that now for 10% of the batch mask images, we'll multiply all channels of those masks with 0. And then all we do is pass this mask as con underscore input. Rest of the code is same. So now let's see some of the results that we get after training a model using this mask conditioning. So because of the mask spatial conditioning, we can see that right from the start, the model always fixes the pose. And that doesn't change during denoising. The model, however, keeps on modifying the finer details. The hair color will also change during denoising because conditioning only tells the spatial location of it. And these results are from a model that is trained together with text and mask conditioning, and it's only trained for about 25k steps, and training also was stopped the moment I started getting okay-ish results, which is evident from the lack of diversity, and even quality is not great, but at least we can see the conditioning being honored and the output quality is not terrible. Let's now look at super resolution and inpainting. For super resolution, we'll again get the latent encoding of the images in our dataset. But rather than training diffusion model on just the noisy latent encodings, we take a degraded version of this image and concat that with the noisy latent. This concatenated output is what is passed as input to the diffusion model. And during diffusion training, the model is learning to generate the latent code based on the degraded input. Then for inference, once we generate a sample of this latent code, we pass it to the decoder to generate the high-res image in pixel space. Through this, if our autoencoder is trained on, let's say, a downsample factor of 4, then the super resolution model will be able to generate images of 4x resolution. Moving to inpainting, where the task is that we have an image and a mask, and the goal is to reconstruct the pixels within the masked region, either based on what's plausible based on the context of image, or condition that reconstruction on a text prompt. In theory, any diffusion model can be used for inpainting without specifically training for it. What we can always do is take the original image, run it through the forward process, generating a sample at each of those noise steps. Then while we are generating a sample from random noise using our trained diffusion model, once we have the denoised image at t-1, we use the mask and inverted mask to combine the two images at t-1, where the inverted mask is multiplied with the noisy version of the original image at t-1, and mask is multiplied with the current denoised image prediction by the model at t-1. Then adding these two together gives us the image that becomes our denoised sample at t-1, which again is fed to the diffusion model to get noise prediction at t-2, and same steps are repeated till you get image at t0. Basically, at each step, we are ensuring that for masked pixels, diffusion model generated samples are used. And for unmasked pixels, a sample from the forward process of original image is used. And for LDM, we'll just do all of this in the latent space and feed the generated latent image to the decoder. For LDMs, we would do this mixing of generated pixel image and original image again after the entire decoding step, but the inpainting process remains the same. And if your model understands text, then you can do guided inpainting. Like here, I'm using a model that was trained using text conditioning on the celeb dataset. And I'm going to compare the inpainted output with the reconstructed image from the autoencoder, so that we can separate the inpainting error from the reconstruction error. So if we look at the inpainting process using this technique, the final image that we get is not too bad. But here the region to mask was actually of a different color. If we apply the same process with masking a random region of the face as well, we'll see that while the reconstruction definitely is not bad, but the pixels of generated regions are not always in harmony with the neighboring pixels of original image. And this issue will further magnify once you work with higher resolution of images and lead to edge artifacts. There are ways to improve the quality. I think in one paper, the authors, after combining the two images, do repeated iteration of adding noise for one step and denoising one step, just to increase the harmony between the reconstructed and original pixels. But the authors of LDM train a model to do the inpainting by giving the model access to original image pixels and fine-tuning it specifically for the inpainting task. So we have our image and mask. We first use the inverted mask to generate a masked version of the original image. This is then fed to the encoder to create latent image for this masked image. We also downsample the mask to the same resolution as the latent image. This is similar to the semantic synthesis task that we saw earlier. Now for training the inpainting model, we take the latent images of our dataset, and like before, the task is to learn to denoise this image. But as input, it now also receives the encoded masked image and downsampled mask. Obviously at inference, the model will receive a random latent noise, but through the training it would have learned to generate the latent image better by making use of the latent code of non-masked region. And that way, when the generated latent is fed to the decoder, it is able to generate better quality image where the boundary regions are better and there is more harmony between the non-masked and masked regions of output. Here I've used the exact same image as output, but the gist is that using the model, the inpainted output would end up to be better quality. And as I had mentioned before, for LDMs, after generation, we combine the original image and the generated image using the mask and 1- mask to get the output image. This is so that the pixels belonging to non-masked regions are exactly same as the original image. Now we are going to step into the final conditioning, which is text conditioning. And the core idea behind text conditioning is cross-attention. But before that, let's quickly look into self-attention again, and from there transition to cross-attention. Feel free to skip this entire section if you are already familiar with self-attention. So assume we have this image, and we are at a layer where this image is now represented by a 2x2 feature map with C channels. The two objectives of self-attention are to identify that out of everything in an entity's context, what exactly is relevant to it. And second, to bake in the representation of that relevant context into the entity's representation. Let's assume we want to do this for the first grid cell. We use three matrices WQ, WK, WV, each of which is C cross attention dimension. So it's merely projecting the existing representation to a new dimension. We use these matrices to get Q, K and V representations, where Q is query, which is the projection of input representation, the entity for which we are trying to compute the relevance of all the context item. So here that is 1. K is key, which is the projection of representation of all context items. So here that is 1, 2, 3 and 4. V is value, which is context representation that we'll use to bake in the context understanding into the input. So K is the context representation used for computing relevance, and V is the context representation that actually gets added to the input based on the relevance computed. Once we have query representation for 1 and K representation for 1, 2, 3 and 4, the relevance for each context item to the input or query is computed using scale dot product. This is just dot product divided by the scaling term, which is only for stability to prevent the product from growing in magnitude. Then we simply compute the relevance with all the context item using their key representation and use softmax so that the relevance values sum up to 1. And finally, with value representations computed using WV matrix, we get the context representation as the sum of product of values of each context item with its relevance. We then project this back to our channel dimension and simply add this to the representation of 1 that we had to begin with. And doing this for all feature map cells is easy, just using matrix multiplication. 4 cross C with C cross attention dimension to get 4 cross attention dimension Q, K and V. Scaled QK transpose then gives us 4 cross 4 relevance values. And then multiplying with value representations gives us 4 cross attention dimension, which is then projected to C dimension and added. I did not get into multi-head attention and how the computation changes for multiple heads, because it's really not necessary here. But in case you want to know that, you can check my attention video on Vision Transformer, where I go into everything in detail. Now moving to cross attention. The only thing that really changes is what the queries, keys and values are. The queries will still be the projections of our feature map cells, but keys and values, instead of being feature map cells, will instead be projections of some context items, which can be text, in which case it will be text embeddings. It can be speech or sound, or even an image, in which case it will be a sequence of patch representations. For our case, we focus on text as an example, but the same applies for any kind of context. So the typical way to get a representation of a text sentence is to pass the words to a tokenizer, which will tokenize the words based on a vocabulary, and then these tokenized indexes are passed to some pre-trained encoder. An example would be BERT encoder pre-trained using masked language modeling. And the output of the encoder would be batch size, cross sequence length, cross embedding dimension. Now let's ignore the batch size for now and assume that the tokenizer returns these 4 tokens. And we get encoder output as a sequence of these 4, each of which have dimension as embedding dimension. So these 4 embedding dimension vectors is our context representation. For cross attention, our goal is still very similar as self attention. We want to identify for a given entity, or here a feature map cell, how relevant each of these text tokens are, and then using these relevance values, bake in the representation of these text tokens into the input. Let's again deal with 1. So our query will be the feature map cell 1, but key and value will be these text token representation. We again have 3 WQ, WK and WV matrices, except WK and WV are now embedding dimension cross attention dimension, because we need to project the embedding dimensional text representation to the attention dimension, since we need to do the dot product. These will be used to build the query representation for 1 and key and value representation for these text tokens. Again, the only point of difference is what is Q and what is K and what is V. Using the matrices, we get the query and keys representation. Same dot product gives us 4 values and then softmax. And like here, maybe the token castle gets a higher relevance. Then we use WV to get value representation of these text tokens. And same as self-attention, use the relevance and value representation to compute the context representation. We have to project this back to the channel dimension, and then like self-attention, we just add this to the existing channel dimensional representation of 1. And obviously similar to self-attention, we can do this for all feature map cells in one shot. So up till now, we have this ResNet and self-attention layers, which are used in all blocks. And now we simply stack a cross-attention layer here, with same normalization and residual connection. That's it. The official implementation also adds feed-forward layers here, but I have left that. Now, as I had mentioned, that we can use the same cross-attention to attend to any kind of input. So say you want to do image conditioning, but not spatial conditioning. Like maybe you want to generate variations of an image. So you can get the representation of an image using something like a VIT as a sequence of patch representations. And then you can use cross-attention here as well. Query will still be spatial feature map representations of the noisy latent image, but keys and values will be these context patch representations. And once the diffusion model is trained, it can learn to use the context and generate an image which has similar content as the context image. Let's now look at the code changes that we do to our diffusion unit to add this cross-attention. We'll again start from the config file. This is for the mask conditioning model that we had before, and our only conditioning type was image. So the only change that we do to make this a text condition model config is in this condition config section. We now have both text and image as our conditioning types. The image conditioning config is exactly same as before, and what's new is this text condition config. This has the text model, which for now we are using BERT. This trained text model is not really used as of now, so let's just skip it. The text underscore embed underscore dim is the embedding dimension of text tokens that the text encoder, here BERT, will give. And this is the condition dropping probability. In our dataset class, we get the config. And while we get the images, we now also fetch the corresponding captions of those images. The repo readme has more details on how to get these captions, but for now it's sufficient to know that each image has a txt file associated with it, which has multiple captions written in it that are corresponding to that image. In our get item, after the image tensor code, we create the cond underscore input dictionary, and now this will have both image key as well as text. And for text, we randomly select one caption from the list of captions that were associated with this image. Let's go to the unit class. For text conditioning, we now need to get the text embedding dimension from the config, and we'll soon see where it's used. But after that, the only change is in the down, mid and up blocks. What we now do is pass these two additional parameters to the initialization call of these blocks. Cross underscore attention, which is just a boolean indicating if text conditioning is required, and the context underscore dim, which is the text embedding dimension. These two are only passed now as they are only needed for cross attention. They are used identically in all blocks, so let's just see their usage in down block to get a sense of what is happening there. By default, cross attention will be disabled, but if enabled, we create new layers in the down block. And all of this is our cross attention block, where we have this context underscore projection, which is just a linear layer transforming the inputs from context underscore dim, or here the text embedding dimension, to the channel dimension. And this just enables us to use the matrix of same dimensions for WQ, WK and WV. And then just like self-attention, we have some normalization and multi-head attention. In the forward method, then instead of layers of ResNet and self-attention, we now will pass the input through layers of ResNet, self-attention and cross-attention. For cross-attention, we'll first get all the spatial elements together, normalize it, and then a transpose, which makes the last dimension as the channels. So essentially we get a h times w sequence of channel dimension vectors. Each block in its forward call receives this context item now, and we feed the past context to context projection layer. So context will be a sequence of text embedding dimension vectors, and now after projection, it will be a sequence of channel dimension context vectors. And then we do the multi-head attention to get the context representation for each of the spatial h times w elements. This is then reshaped so that it can be added to the c cross h cross w existing feature map representation, and then we just add them both. So this entire section is the new part, and this cross attention layer is added for all the layers that we had. The same thing happens in other blocks as well. Going back to our unit, in the forward method of unit, this was all the code that we did for mask conditioning, this for class conditioning, and then for text conditioning, we just get the text representation from cond underscore input. The dataset just passes captions, so it will be the training code, which we'll see later, that will convert the captions to text encoder representation. But ultimately the model in here receives the text encoder representations of shape batch size, cross max sequence length, cross text embedding dimension. Then all we do is that while calling all the blocks, pass this as the context. And like we just saw, the blocks will use this context to do the cross attention. In the training code, we actually have quite a few changes now. This section gets the condition config, and if text conditioning is present, it loads the tokenizer and text model. We also call the model to get a representation for this empty text, and we'll soon know why. This get tokenizer and model method uses the config and gets a pre-trained encoder using the Hugging Face transformers library. And you can use any encoder here. The other guy simply tokenizes the input text, which at the moment is empty text, and gets the last layer's hidden states from the trained encoder for this tokenized text. Now jumping to the training loop, this part is same. This bunch of code we added for class conditioning, this for spatial mask conditioning, and now this is the part for text, where we get the captions for the batch from the _" input that the dataset returns, use the text model to get the text encoder representation for them, and then we get the conditioning dropping probability. We call this utility method with the encoder representation of captions and empty text representation. And inside this, again for a fraction of batch items, we simply replace the existing caption representation with this empty text. So for text conditioning, this empty text acts as a no conditioning information for the model. This then becomes the _" input that the UNet model receives. And after that, everything else is the same. I have trained only one model, trained with both text and image conditioning, and that too for the least number of steps that give me okay results. So the results of text only generation will not be that great, because the model would have further seen them only 10% of the times. But these are some cherry-picked results. And like we had seen, for generating image using only text, we can just pass the all 0 k-channel mask. The results with mask as well as text are quite better, and with text you can guide the generation to a particular direction. The model is good at honoring features like hair color and smile mentioned in text, because the dataset has a lot of captions containing them. But things like hat, glasses, earring, it's not great at them, because they are very infrequent. And of course it would get significantly better if we continue training this. Okay, so I've covered almost everything that I wanted to on conditional LDM. Now let's see what it takes to get to stable diffusion from here. And actually not much at all, at least not from implementation perspective. Stable diffusion is really just a latent conditional model with a specific choice of text encoder, which is the text encoder of clip. And it's just that during cross-attention, the diffusion model learns to attend to clip text embeddings. And the official repo's README has more details on how the different versions of stable diffusion are trained. You might already know about CLIP, but in case you don't, it's a model by OpenAI and is short for Contrastive Language Image Pre-training. And essentially the way it's trained is that we have a text and image encoder. These can either be trained from scratch or fine-tuned from existing pre-trained versions. Then given a dataset of image-text pairs, we take a batch of n such image-text pairs. This gives you n square all possible text-image pairings. And then we train the model to project the text and image representation onto a joint space, such as to maximize the cosine similarity between the text and image representations of the n actual matching pairs. And simultaneously for the n square minus n unmatched pairs of text and image representations, we train the model to minimize their cosine similarities. And because of being trained in this fashion, one could argue that the text representation captures some notion of visual appearance. Kind of similar to how hearing the word apple generates a visual image in your brain. Maybe this, or it could be this as well. But let's assume it's the fruit for now. Now if all your life you had just read about apple and never seen it in real life or in an image, then while you would have established some notion of apple being a fruit and red in color and its shape, you might find it difficult to associate the word apple to something visual, at least when compared to the scenario where you have actually seen it. So similarly, representation of a text encoder trained purely on language task might not have the same ability of associating words with visual appearance than something like CLIP. The argument could also be made that after seeing more and more data, even if it's just in text form, the association will get better. But hopefully this gave you some intuition as to why CLIP text encoder might possibly have an advantage as far as the task of image generation is concerned. I found this paper which actually goes through a bunch of experiments and attempts to compare BERT text encoders with clip text encoders. So do give it a read if you are interested. And they indeed find through experiments that while purely from a text understanding metric, BERT text encoder was better, but clip's text encoder was able to better associate a text and its visual appearance. Now let's implement the change of encoder to clip in our code. And as I had said, it's not going to be much because we anyway separated out the text encoder initialization. So this was the utility method that gave us our tokenizer and model. And all we do is change this part to this. And you can use a different version if you want. And all you need to do is change the name here. And now we can just move to the config and change the encoder name in the config as well. And also because the dimension of this encoder's hidden state is 512, so we change that as well. And we are done. At least theoretically, we have implemented all parts of Stable Diffusion. So this video ended up being a long one as we went through different types of conditioning and saw in detail how each of them are implemented. Of course, this implementation would not be the most efficient one, and if your interest is in getting best results, I would suggest to use the official repo or the diffusers library. The repo that I have created is more of an attempt to extract the most important parts and make sure that one can easily understand them and what's happening within them by going through the code. Thank you so much for watching this video, and if you think these videos are worth your subscription, do subscribe the channel and like the video.